Hello everybody and welcome to ECMath. Today we're going to look at something called a geometric sequence and then later on a geometric series. So what is a geometric sequence? Well, it is a sequence of numbers where each term in the sequence is multiplied by the same constant non-zero number to get the next term. A geometric sequence always has that constant common ratio between consecutive terms. Here are, right in front of us, 4 examples of geometric sequences, and let's just take a second and look at them and look at their behavior. So to go from the first term to the next term, or from the second term to the third term, or from the third term to the fourth term, there's always a constant multiple. They're multiplied by the same number every time. And in this first sequence, it looks like you're multiplied by 5 every time. That appears to be the ratio. From 4 to 8 to 16 to 32 to 64, that appears that we're multiplying by 2 each time. Now this can get a little weirder, right? Down here we have some negative numbers. What's going on here? So I want to give you kind of an approach for finding the common ratio if you have to. And the approach is actually built into the name. It's called a common ratio, which means that if you take any 2 consecutive terms, an, and divide it by the term before, an minus 1, that will always, for that given sequence, give you the same ratio. So let's check that out. For the first sequence, first term, second term divided by the first term is 5 over 1, which is 5. Third term divided by the second term, 25 over 5. Oh, that's 5. We could do 625 over 125, get those last 2 terms that are on the page. That's going to be 5 as well. So the ratio here for this first one is definitely 5, which is kind of what it looked like. That's what we thought. But it's nice to have a way to divide terms to be sure. And if you're ever not sure what the ratio is, just find 2 consecutive terms, put them in a ratio, and see what you get. And that should always be the same, right? It was actually important that we got 5 every time. It's not geometric if you have the ratio sometimes it's 5 and sometimes it's 6 and sometimes it's 4. It always has to be the same constant number. So let's go ahead and find the rest of these constant ratios. So for the second one, we could do 8 over 4. That's 2. Let's check another one. 64 over 32. Oh, that's also 2. So in this case, the ratio appears to be 2. Let's check the third sequence, 6 to negative 12 to 24 to negative 48 to 96. So it appears sort of like it's doubling, right? You're going up by a factor of 2, but you're switching signs every time. And we can actually do this by multiplying by a single number. It just happens to be a negative number. So let's compute the ratio just using our tool. So negative 12 over 6 is negative 2. That's going to be the ratio. We could check some other terms. Negative 48 divided by 24. That's also negative 2. So it seems like our constant common ratio for this sequence is not 2, but negative 2. And that's how you get an alternating geometric sequence. And that's something that can happen with geometric that couldn't happen with arithmetic because you're multiplying, so you can be flipping signs. For this next one, we seem to be decreasing now in terms. Everything else was increasing, and you can be decreasing. You can go 9, negative 3, 1, negative 1/3. Oh, this is interesting. So it's tempting to say, oh, it looks like I'm dividing by 3 in these cases, but remember, we're looking for a multiple, a constant multiple. So it's better to set up a fraction and say, okay, consecutive terms, negative 3 is after 9, and that reduces to negative 1/3. And that's going to be the ratio here. And notice that we had the alternating, that's accomplished by the negative, and the sequence is decreasing because we're multiplying by a fraction every time. So whenever your ratio is a fraction, you're going to have a decreasing geometric sequence that gets probably closer and closer to 0. Why don't we check some other terms, right? You should always check a couple terms just to be sure. We could do 1/9 divided by negative 1/3. Ooh, this is getting interesting. Now remember how these fractions work. That'd be the same as 1/9 times negative 3 ones, that is negative 1/3 as well. So we do have a constant ratio. We've checked a bunch of terms. That's how you find your common ratio. Take the 2 consecutive terms and put them in a fraction. What if we're given the ratio and we're asked to write some terms? Well, that's not so bad. You can just write out the first term, A1, that's 36, and then you just multiply by the ratio every time. So 36 times 1/3, that would be 12. A3 is going to be 12, the previous term, times 1/3 again. This is kind of using almost like a recursive definition. Well, 12 over 3 is 4. The fourth term would be 4 times 1/3. Okay, now it's just going to be a fraction, so 4/3. And the fifth term would be 4/3 times 1/3, or 4/9. So again, we had a fractional ratio, so our sequence is decreasing down towards 0, even though our starting term was fairly large. And that would be the first 5 terms of the geometric sequence. Now, we'd like to have a formula for the general term. Like, if I wanted the 12th term, I don't want to have to write out 12 whole lines of a sequence, but I want to look at the work we've done here, see if it can help us find that formula for the general term. So let's take apart this fifth term, and I wrote it as 4/3 times 1/3. But if I think about it, where did 4/3 come from? Well, that was 4 times 1/3. And where did 4 come from? It was 12 times 1/3, and it was 36 times 1/3 was 12, and that's where that came from. So if we think about this enough, I could also probably express this 4/9 as 36 times 1/3. Now, how many times have I multiplied by 1/3? Well, it looks like I multiplied every time I went from a term to another term. So there's 5 terms, but I switched between terms 4 times. So this is going to be 36 times 1/3 to the 4th. And it's got that pattern. If this was the 5th term, then this seems like it's going to be something like n minus 1. And it seems like we're multiplying by the ratio. That makes sense. And it seems like this is that initial value, A1. Hey, this is starting to feel like a general formula or something you could generalize. That actually is the formula for the general term of a geometric sequence. An is equal to the first term times the ratio to the n minus 1 power. And to be a little more formal about why that's the formula, well, let's just think about the sequence an. That's geometric. The first term is a1. The second term is a1 times the ratio 1 time. The third term, we just multiply by the ratio again, so I'll write it as a1 times r squared. And the fourth term, well, I'm just going to multiply by the ratio again, so that's a1 times r to the third, and so on. And so because we've only multiplied by r one less time than the term that we're on, since we didn't multiply by r on the first term, this is like an r to the 0 here, I guess you could say. This is r to the n minus 1. That's the general term of a geometric sequence. I hope this seems at least a little bit familiar to you, because this should look a lot like the exponential function y equals ab to the x, or whatever format you've learned that in before. It has a lot of similar properties. You're multiplying by the same constant number every time. At this point, it's good to pause and do a little comparison of the two famous kinds of sequences that we've looked at now, arithmetic sequences and geometric sequences, because they are easy to mix up. So I've tried to put everything into a helpful table. In an arithmetic sequence, which we learned about in the previous video, by the way, each term is a constant difference added or subtracted from the last term. And in a geometric sequence, each term is multiplied by a common ratio to get to the next term. There are general term formulas. For arithmetic, it's a1 plus the difference times n minus 1. And in a geometric, it's a1 times the ratio to the n minus 1 power. So instead of adding and multiplying, we're multiplying and exponentiating. These map with the familiar functions you know and love, the linear function mx plus b, and the exponential function ab to the x. The only difference is that sequences are only defined on the integers, so their graphs look like this, where the graphs of functions look like this. The shape is the same, but the type of graph differs. Let's also take a minute and think about maybe why these sequences have the names that they do. An arithmetic sequence, why does it have that name? Well, it turns out that if you have three terms in sequence, I just called them A, B, and C, the middle term is the arithmetic mean. We know that as the average of the other two terms. So if my arithmetic sequence with a common difference of +4 is 3, 7, 11, if I take the average of 3 and 11, I get 14 over 2, which gives me 7. That's the middle term. On the other hand, there's this other kind of mean, not the arithmetic mean, but the geometric mean. And in a geometric sequence, the middle term of any group of three terms is the geometric mean of the other two terms. The geometric mean is instead of adding and then dividing, we multiply the two numbers and then take their square root. In our geometric sequence 5, 25, 125, where the ratio is times 5, the geometric mean, 5 times 125, under a square root, root 625, is 25. So the geometric mean is the middle term. And that's why this is called a geometric sequence. It's not because it is particularly involved with shapes or anything, although there are some pretty nifty shapes that you can create to understand these, but it's really just has to do with this term, the geometric mean versus the arithmetic mean. And that's all. Let's look at an example. Going just back to that general form. So let's write the general term in the sixth term of a geometric sequence, where the first term is 14 and the ratio is -1/2. While we're here, we can start to list out the terms just to get familiar. So it would be 14 would be the first term, and then I would multiply by -1/2, so it would be -7, +7/2, -7/4, etc. I guess I could probably just keep going until the sixth term, but I want to write the general term. So we know that the general term is the first term times r to the n-1. So the general term in this one would be 14 times -1/2 to the n-1. That's the general term. And to find the sixth term, I would do A6 is 14 times -1/2 to the 5th. And if I'm computing this by hand, well, I know what 2 to the 5 is. It's 2, 4, 8, 16, 32. But because it's negative, it's going to be -1/32, because it's also a fraction. So it's going to be something like 14 times -1/32, which should probably give me something like -7/16. And we can see, does that match with what we would expect in the pattern? And yes, it does, because we'd go to 4, then 8, then 16. So that would be a good sixth term. And then for a last example, we have sort of a mystery sequence, and this is where these problems start to go. Once you start to recognize the basic pattern, you can start to mix up the givens and the different pieces of information and make all kinds of interesting problems. So this is kind of a slightly more advanced problem. Here's a geometric sequence. What was the first term? It might, again, feel like, oh no, I only have 2 data points. That can't be enough, but I do know that this was a geometric sequence, and that's really important. In fact, that's all you need to know along with these terms. So let's think about what makes a sequence geometric. Well, it's geometric if we multiply by some ratio as we pass between terms. So to go from 16 to 250, I would have had to multiply by that ratio, which I don't yet know what it is, by that ratio 3 times. So the fact that I've done this means that I can write an equation. I could write 16 times r times r times r must equal 250. Move that here. Now that's something we can solve with algebra. It does help. You know, when we're dealing with exponents, it's nice to have a calculator. So we'll go ahead and get that out. So that's about 15.625. But that's equal to r to the third. So I need a way to get rid of that r to the third. Well, remember how you get rid of an exponent like this? Is you take the matching root. So we're going to take the cube root of both sides. Or we could take both sides to the exponent of 1/3. And that's actually what I'm going to do in the calculator because it's easier to find. So I'm going to take that answer and I'm going to raise it to the power of 1/3. And that should give me the ratio, which is 2.5. So the ratio r is 2.5. Okay, well, I've circled that, but is that my answer? No, because I was asked what was the first term. Well, why don't I actually check just that this ratio is good, right? We've been talking about how to check your answer. Well, one way to check that this worked is you can do 16 times 2.5 and see what you get. Okay, that would be 40. So that says that'd be the next term. That would be 100. And times 2.5 again would give me 250. Do it again, you get 625. Okay, so that seems like I have found the right ratio. Now how do I go backwards? You just divide. Let's go back to 16 and divide by 2.5. You get 6.4, and that is what the first term must have been, 6.4. And you do it by finding the common ratio and then solving around. There's actually a lot of other ways to approach this problem, and I'd like to take a minute. We've solved it, we know the answer. Take a minute and share with you what some of those ways are, because, the more ways you have to talk about a problem and look at it, the better of a problem solver you're going to be. So one approach to this problem is just to say, okay, well, I'm going to think about it sort of algebraically, and I know that the second term is 16, and the 2, 3, 4, 5, fifth term is 250. I also know the general term for a geometric sequence is given by a1 r to the n minus 1. So if I know a2 is 16, I could write 16 is equal to a1 r to the n minus 1. Well, that would just be 1, right? Because it's 2 minus 1. And I could also write that 250 is equal to a1 r to the 4, because it's 5 minus 1. And then I have two equations and two unknowns that are the same, right? A1 and R. And I could solve it like a system. You could maybe put those in a ratio or divide them or subtract them or something. To solve these, I usually like to put them in a ratio. So you could say, all right, 250 equals A1R to the 4. Divide that by 16 equals A1R to the third. R to the first. By the way, you can do this as long as you make sure that none of your terms are 0. You get, 250 16 is 15.625 is equal to r to the third. Hey, and that's the same equation we were solving earlier. So that's one way to solve this, just kind of using like more algebra than understanding of sequences. You're going to get the same result. And then a third sneaky way to look at this problem would just be to forget what the problem was for a second and just say, well, wait a minute. You gave me the second term, but what if we pretend that that's the first term, right? It's 16 blank blank 250. I'm going to pretend that that's the first term, and then we can set up 250 is equal to, well, and if I'm pretending that this is 16 is the first term, then I just write 16 r to the n minus 1, but that's now the fourth term, so I'd write it as r to the third. 250 equals 16 r to the third. Just thinking about it as a sequence, we'll find the ratio, and then we could go back and solve the original problem. Those are three different approaches. I mean, they end up doing the same algebra, but slightly different way of thinking about it to the same problem. All right. In conclusion, geometric sequences have a constant common ratio. They are like exponential functions, you multiplying by the same thing every time. To find that ratio, you can divide terms that are in sequence. The later term divided by the term before it. You should always get the same thing no matter where you are in the sequence. If you have a alternating sequence, positive, negative, that means your ratio is a negative number. One other thing I didn't write here is that if you have a ratio bigger than 1, your sequence will grow. Less than 1, your sequence will shrink towards 0. I mean, unless it's alternating, but it will still sort of, the magnitude of the sequence will shrink towards 0. And then, of course, there is our general term equation. an is equal to a1r to the n minus 1. Now, all that's said, it sounds very simple. These can be really complicated, depending on what you're given and what you know and what you don't know. As long as you know your terms, you know everything that's going on, you will be able to solve any problem in this section, I promise you. Now, the next question is what happens when we start adding up the terms of the sequence? Stick around to the next video and find out more.